Hi AP Stats, this is Mrs. Harding. This is the video that goes along with lesson 7.2. What I'm going to go through with you is a discussion of the sampling distribution of a sample proportion. Lots of vocabulary there to keep track of. But on the screen, what you're going to see are the three learning objectives or learning targets for this. The first one, calculate the mean and standard deviation of the sampling distribution of a sample proportion p hat and interpret the standard deviation. The second, determine if the sampling distribution of p hat is approximately normal. This is going to be a set of conditions that you're going to have to check. And then in the last one, if appropriate, use a normal distribution to calculate probabilities involving p hat. So you're going to need to go back and apply a normal distribution to some of your questions. So the activity you can find in your OneNote notebook, again, this is section 7.2. So go ahead and flip to that in your OneNote notebook. Here is what the activity looks like. So just to kind of read through the top there a little bit and help you with some vocabulary, it says, what proportion of U.S. teens know that 1492 was the year in which Columbus discovered America? A Gallup poll found that 210 out of a random sample of 501 American teens aged 13 to 17 knew this historically important date. The sample proportion, p hat, is 210 out of 501. That's the proportion of success within the sample. This is the statistic from the sample, and we're going to use this to gain information about the unknown population parameter, P. Since another random sample of 501 teens would likely result in a different estimate, we can only say that about 42% of U.S. teenagers know that Columbus discovered America in 1492. So what we're going to do in this section is clarify what we mean by about. So in here, we're going to be referring to an applet that I'm going to show you on my screen. There at the top of my screen, you see, it says, how good is the statistic p hat from our random sample as an estimate of the parameter p? Now remember, the parameter is the proportion of the population, and the statistic is the proportion from the sample. That's what p hat is versus p. To find out, we ask what would happen if we took many random samples. So remember, every random sample will give you a slightly different proportion. So if I did another sample of 501 teenagers, my proportion of success will be slightly different. So what would happen if we did many random samples? Well, that will give you the sampling distribution of p hat. So how do we determine the shape, center, and spread of the sampling distribution of p hat? We're going to start here with this simulation on Reese's Pieces. If you want to just take a look, start there at the bottom in part A and B. I'm going to just be having the applet on the screen as I go through the questions. So you'll probably want the questions on your screen listening to me go through the applet. Okay, there on your screen is what the applet looks like. If you wanted to do this yourself, you can see the web address up there in the top. So we're going to go through each of these parts, and I'm going to demonstrate it right on my computer so you can see how the graph is going to change. But in part A, it says click on the Draw Samples button. An animated simple random sample of n equals 25 candies should be dispensed. Okay, so my probability of getting orange was actually 45. And I'm going to change this right here to proportion. So if I draw samples, it does one sample of 25. And in that sample, you can see the proportion of success or the proportion of orange candies. It wasn't exactly 0.45. Every sample will be slightly different. It is 0.48. And then you can see down here in the graph, let me scroll here a little bit, it put a dot there at 0.48. So 0.48 is one sample proportion that we're going to use to graph a sampling distribution. So then part B, change the number of samples to 9. Okay, so let's change this to 9 and click Draw Samples so that we have a total of 10 samples. And you'll watch the applet go through all these samples. We won't animate everything. But you can see after each sample is drawn, I guess it doesn't put it on until the very end of all 10 samples. So we'll just wait a second here while it finishes it. I guess I should have unclicked the animation, huh? Okay, there we go. All 10 are in there. So you can see the 10 dots. One dot on the sampling distribution is one sample of 25 and what the sample proportion was, what p-hat was. And you can see that the most recent one had a sample proportion of only 0.36. So in part B, what is the standard deviation and p-hat of this? Well, everybody's answers would be a little bit different because we would just be estimating where the mean was and what the variability would be. Go ahead and flip the page to part C. It says to take more random samples quickly, enter 390. So we're going to do a total of 400 samples. I will definitely take off the animation this time. So when it draws samples, you're just going to see a bunch of dots. So if you look at this, if you had to describe, let's see, part C says, describe the shape, center, and spread of the approximate sampling distribution of p-hat. So this is 400 sample proportions. You can see the most recent one, p-hat is 0.4. And if you were to describe the shape, center, and spread, it's approximately normal. The mean probably is not too far off of 0.45. And the standard deviation, possibly around 0.1, 0.15. It would just be an estimate on your part. Part D, how do you think the sampling distribution of the sample proportion p-hat will change if the sample size is changed to n? So think about that for a second. In each of these samples, I was drawing 25 candies and finding the proportion of oranges. What do you think would happen if instead we drew 50? What will happen to the shape of this? Some of you might remember increasing the number of things in the sample, what that does. So we're going to reset this applet and actually find out. So we're going to keep the probability of success at 0.45. We're going to do 400 samples of size 50. And then draw the sample so you can take a look at the partial sampling distribution there. And you should notice it is probably expected. It's approximately normal, still a mean somewhere around 0.45. But this time, you might not remember exactly how far out this went. But what you should notice, if you could compare those two scales, is that this actually has a smaller standard deviation. So the highest points up here are at about, 0.62, and the lowest point here is about 2.6, 2.7. So doing that actually decreased the standard deviation. So part E, how would the sampling distribution of p-hat change if the proportion of orange candies in the machine was p equals 0.15 instead of 0.45? Does your answer depend on whether n equals 25 or n equals 50? So we're going to do both of these on here. So what would happen, let's reset it, if instead the proportion of success or proportion of orange candies was only 0.15, and let's say we did sample sizes of 25. Okay, let's take a look at this. All right, in here, there might be just a slight skew right on that. It varies from 0 to about 0.36. So what happens then if I change this and I do a sample size of 50? So now each dot represents the proportion of orange candies out of 50. All right, it's a little more normal. There's still some slight skew up there. And it varies from 0.04 up to about 0.32. So it's maybe a little bit less. So you can see in the answer key for this says, yes, the shape becomes more normal as n increases and standard deviation of p-hat decreases as n increases. And that's kind of an important concept for you to think about. The larger the sample size, the more normal the sampling distribution of p-hat is, and the smaller the variation is. It decreases the standard deviation of the sampling distribution. So part 2 says use the applet to discover the effects on the distribution by changing both values of n and p. I'll leave this up to you if you wanted to go in and play around with this applet. I'm not going to do it here on the video. But what you will discover is that the distribution is approximately normal when NP and n times 1 minus p are both at least 10. And you're going to recognize that as something that we talked about when we did binomial distributions also, that the expected number of successes and failures are both at least 10. All right, so if you go to the bottom of page 2, it's got a little summary of what you should have seen from playing around with that applet. The shape. So we're talking about the sampling distribution of p hats. The sampling distribution, again, every dot on the sampling distribution is the statistic from one sample. So all of the dots are a proportion of success in one sample. So the shape, in some cases, the sampling distribution of p hat can be approximated by a normal curve. This depends on the sample size and the population proportion p. The center of the sampling distribution, take note of the notation there, that's mu of p hat, is equal to the population proportion. So remember in the applet, when we were doing the Reese's with the orange candies, the center of our sampling distribution in the beginning seemed to be roughly about 0.45, which was the population parameter. On the next page, the spread, the variability, the standard deviation. For a specific value of p, the population parameter, the standard deviation of the sampling distribution gets smaller as n gets larger. To sort out the details of shape, center, and spread, we need to make an important connection between the sample proportion p hat and the number of successes in the sample. So I'll let you take a look at what it says there in 3a. But think about this as a connection to a binomial distribution. In a binomial distribution, we were counting the number of successes. In a sampling distribution of p hat, we are looking at the proportion of successes. So if we have random variable x that is binomial, x is the number of successes, you can see right here then that p hat is actually the number of successes, which is x, divided by the sample size of n. So this sampling distribution of sample proportions is sort of a transformation of the random variable x. And if you remember from your last chapter, sorry for all the there, there I go again. Hopefully I'm giving you a good laugh while you're listening to this. The mean and standard deviation when you apply a transformation to a random variable are both affected by dividing by a constant. So remember, n is the sample size. So I could take the expected number of successes divided by n to get the mean. I can take the standard deviation of binomial random variable x and divide it by n. And here on the screen, it might not be totally obvious to you how those two connect to each other. So I will draw something really fast that I think will help you. np times 1 minus p. N could be thought of as the same thing as a square root of n squared. So then this is np times 1 minus p over n squared, crossing off an n. So you might be thinking, am I going to have to work through that every single time? And the answer is no. These are formulas that you will just apply. They'll be on the formula sheet. All right, so take a look at the next page. We're going to start getting into some examples here. So at the top, it says choose an SRS of size n from a large population. Let p be the proportion of successes in the population and p hat the proportion of successes in the sample. This is going to sound also familiar from binomial random variables, because when you're sampling without replacement, you have actually altered your proportion of successes in the population that you would be choosing from. But as long as we maintain our sample size to be less than 10% of the whole population, we can still apply these procedures. So it says there, if the conditions of NP is greater than or equal to 10, oops, sorry, I read a little too far down. It says the mean of the sampling distribution of P hat is still the same as the proportion of success if the 10% condition is met. And you can apply the standard deviation as long as the expected number of successes and failures are both 10. So what we're setting up here is before you do any calculations, with these sampling distributions, there's a set of conditions that you need to check and verify are true before the process that we're going to talk about is valid or not. Part D is just kind of a side comment. Consider the formula for the standard deviation of the sampling distribution of a sample proportion. Explain why the standard deviation decreases. Go back and look at that standard deviation formula. When you divide by n, dividing by a bigger number results in a smaller value. So just a real quick reference there to the standard deviation. Okay, so let's talk about a new scenario and see how we're going to apply these conditions. It says we now know most of the details of the sampling distribution of a sample proportion, so let's put them to use. Question number 4, the 2001 Youth Risk Behavioral Study questioned a nationally representative sample of 12,960 students in grades 9 through 12. Of these, 3,340 said they have smoked cigarettes at least one day in the last month. So what is p-hat? Well, p-hat is our proportion of success within the sample. So they gave you those numbers right there. So the proportion of success, I'm doing air quotes here as I talk about success. I don't think smoking as a child is a success. But it's 0.2577. Before we can actually draw any conclusions about what that means or the likelihood of getting a sample like that, we have to check if the conditions of inference apply to this scenario. So let's go through each of these. The randomization condition. We want to make sure that this is a simple random sample of the population. Yes, it states that the study questioned a nationally representative sample. This one gets a little fuzzy sometimes because we often assume that it's a simple random sample even when not specifically stated. But when they say that they questioned a nationally representative sample, you can check off that condition as met. Moving to the next page, the 10% condition and independence. Are the responses and values in the sample independent of each other? So this is referring to having an unbiased estimator. So yes, 12,960 is easily less than 10% of all 9th through 12th graders. So we can assume that the mean of the sampling distribution of p-hat is the same as the population proportion. And then the normality condition. The sample has to be large enough so that NP and N times 1 minus P are both at least 10. And this allows us to apply the normal distribution and calculate the standard deviation of the sampling distribution. They are both easily at least 10. All 3 conditions are met, so we can use normal calculations with the mean and standard deviation of the sampling distribution for p-hat. So if you look here in part E, find the mean. Well, the mean is the same as the population proportion, so that's 0.25. The standard deviation, we're going to use the formula to calculate that, is 0.0038. So we are talking about a normal distribution with parameters 0.25, 0.0038 as standard deviation. And if you flip to the next page, there is a little normal distribution sketched out there for you. It says now we know that the sampling distribution for p-hat follows a normal distribution. Sketch the sampling distribution. That's what this is right here with a mean and standard deviation. Find the probability that at least 25.77% of 9th through 12th graders in a sample size of 12,960 will have smoked cigarettes at least one day in the past month. So this is sort of checking the likelihood of getting the sample that was discussed. And you can see here, calculating Z and determining what that probability is. So assuming 25% of all 9th through 12th graders nationally have smoked cigarettes at least once in the last month, there is a 2.12% chance that in a random sample of size 12,960, that 25.77, that should be a 7 there, % or more of the sample will have smoked at least once in the last month. Okay, so at this point, I know I've been talking really fast trying to get this in 20 minutes or less. Probably won't make it. But here at the end, there is a sample problem to check how well you can apply these concepts. So at the top here of page 7, it has a picture of a normal distribution, sampling distribution for values of p-hat. I want you to pause the video at this point, and I would like you to complete the check your understanding questions 1 through 6, and then we'll check through your answers. So go ahead and hit pause and work through those questions. All right, let's just run through the answers really quickly and then we'll be done. What's the mean mu of p hat of the sampling distribution? It's the same as the population proportion, 0.75, given in the problem. Find the standard deviation. You just need to apply the standard deviation formula. Is the sampling distribution of p hat approximately normal? Yes, NP and n times 1 minus p are both at least 10, so we can assume that it is a normal distribution. Question 4, sorry, it's a little squished in here with the answers. It says if the sample size were 9,000 rather than 1,000, how would this change the sampling distribution? Well, remember, when you increase your sample size, what you're impacting is the variation of the sampling distribution. You're impacting the standard deviation. So if I have a sample that is 9 times bigger than the previous sample, remember this is the square root of a fraction over n. So that would result in a standard deviation that is 3 times smaller. So if n is 9 times bigger, the standard deviation will be 3 times smaller. And then question 5, what's the probability the sample of size 1,000 has a probability greater than or equal to 0.78? Well, we've already established that it's a normal distribution. Find your z-score for 0.78. Find the probability that z is greater than or equal to 2.19. And we get 0.0143. So there's a 1.43% chance of getting a sample of 1,000 people where the proportion of success is at least 0.78. So then how are we going to interpret that? Look down here at question number 7. Should that cause a person to question the original assumption? And the answer is yes. We built this normal distribution on the assumption that the proportion of success was 0.75. So this sample that we ended up getting, well, the probability of getting a sample as extreme as ours was only 1.4%. Now, that doesn't mean that it can't happen, so you don't ever want to say, no, this is impossible to happen. It's just that it's a very, very small chance of getting a sample with that proportion of success in it. So this would cause us to question the basis of the normal distribution that we use to make these calculations. And that right there brings us to the end of 7.2. I talked pretty fast, but tomorrow during class, we will just spend time reviewing what questions you have about this and spending time working on the homework associated with this. I hope you all have a great day. I will see you tomorrow.